Hello, this is FlippedHarber for Algebra 2. In this video we're going to cover section 6.5, finding real roots of polynomial functions. Here's our objectives for this lesson: to identify the multiplicity of roots and to use the rational root theorem and the irrational root theorem to solve polynomial equations. Here's our outline for the video. We're going to start by factoring to solve polynomial equations. We'll talk about multiplicity. We'll talk about the rational root theorem. We'll identify the roots of a polynomial equation. We'll talk about the irrational roots theorem and identify all the roots of a polynomial equation. Now, factoring to solve polynomial equations is a pretty good way to solve a polynomial equation. Sometimes it's the easiest way to do it. We do this a lot with quadratics. We're very used to factoring quadratics in order to solve them. And I need you to remember all through this section that for every factor there's a root. That is, for every factor to a polynomial there's a solution to the polynomial equation. Let's go ahead and factor this quadratic. Let's go to factor to 2x plus 1 times x minus 5. And now to change those factors into solutions, basically I just set each factor equal to 0 separately, and I solve the two little baby equations that I've created. I get x equals -1/2 or x equals 5. So each of my factors, 2x plus 1 and x minus 5, creates a root or creates a solution to this equation. We're going to factor this one like a quadratic. Now the reason I can do this is because this power on the front is double this power in the middle. Okay, you probably wouldn't recognize it right away as something that you can factor as a quadratic, but we can because it's x to the fourth and then x squared and then no variable. Okay, whenever you see x to the fourth, x squared, and then no variable, you should think, maybe I can factor this like a quadratic. Now when I factor it like a quadratic, I don't have x minus 1, I have x squared minus 1 and x squared minus 4. Now each of these can be factored further. They're actually both difference of squares. So I'm going to factor them as such, and you need to know how to factor a difference of squares. X squared minus 1 becomes x minus 1 times x plus 1. X squared minus 4 becomes x minus 2 times x plus 2. Now each of these factors creates a solution or creates a root to the equation. I get x equals 1 or x equals -1, x equals 2 or x equals -2. When the factor is simply x plus or minus a number, like we see all the way through here, the root is just opposite the number that's with the x. Now, multiplicity refers to how often a factor or its root occurs. Now, I'm not going to ask you to factor this polynomial. I'll show you what it factors into, but it's going to factor into the same thing multiple times. Thus, the idea of multiplicity, meaning that it occurs more than once. This actually factors into x minus 2 times x minus 2 times x minus 2 times x minus 2. So we say that the factor, or the root, x equals 2, has a multiplicity of 4, just meaning that it occurs 4 times. Now, I'm not going to bother to read this word for word for you, but here's the rational roots theorem, and pausing the video right now and writing this down would be a good idea. Okay, so let's talk about what all of this really means. Here is a polynomial. We are going to factor the constant at the end, this 6, to create what we refer to as p terms. We're going to factor the leading coefficient, this 2, and those are going to be what we call q terms. Now our p's are plus or minus 1, 2, 3, 6, the factors of 6. Our q values are plus or minus 1 and 2. Now what we're going to do is we're going to take each p value and divide by each of these q values. So we're going to take 1, 2, 3, and 6 and divide by 1. Then we'll take 1, 2, 3, and 6 and divide by 2. Now if there's any repeats, it doesn't really mean anything if there's a repeat, so don't list repeats. Now what I mean is when you take 2 divided by 2, you're going to get 1. Well, that's already covered with 1 divided by 1. When you take 6 divided by 2, you're going to get 3. But that's already going to have been covered. So repeats don't really add anything to us. So don't read too much into repeats. Just don't bother to list them multiple times. Now, some limits on the rational root theorem. It's a rational root theorem, so it won't find irrational roots. We will look at how to test these values quickly. And in order to get started with the rational root theorem, there has to be a constant term. Now, I've changed our polynomial slightly. Notice there's no constant at the end. The way we deal with this is we factor out a variable first to get a constant all the way at the end. Now, when we do this, x equals 0 is a root. X is the factor, x equals 0 is the root. So don't forget that when you're all done with the polynomial. Now I would run my p over q's with the 6 and the 2. Okay, let's go back to our example though. We've got our p values, we've got our q values. Here are our p over q values. I know this is supposed to say p over q. I forgot the q. But basically this is a list of numbers that might work. Definitely not all of them are going to work. And here's the really scary thing, honestly. None of these might work. That would really suck if none of them work. And they're going to be set up so that at least one of these are going to work for you. Maybe even more. At least one of them is going to work in your homework. So relax a little bit, but the problem is finding the one that works. Now, what I could do is I could take each of these numbers, plus 1, plug it into my polynomial, see if I get 0. Negative 1, plug it in, see if I get 0. And keep on going until I've tried and I've eliminated all of them that I can. That's a lot of work, and there's technically a better way to do it. We're going to actually use synthetic division. And I want to start with one that doesn't work. I'll show you one that works. Obviously, I want to start with one that doesn't work. This is what you're not looking for. So I'll tell you right now, 1 does not work. Okay, if you plug 1 into the equation, you do not get 0. But here's how it works, or shows that it doesn't work, with synthetic division. I put 1 in my corner box and I do the whole multiplying and adding and stuff. I'm looking for 0 right here. I don't have 0. So that's what tells me that 1 does not work. Okay. Now, since 1 doesn't work at the beginning, it's not going to work in the middle, it's not going to work at the end. 1 does not work. Okay. Don't try it again. Let's take a look at one that does work. Negative 1 will work. If you plug negative 1 into this polynomial, it will equal 0. The way that gets shown in synthetic division is I have a 0 over here for my remainder. Now, why is this better than just plugging in negative 1? You could have plugged in negative 1, showed that it equals 0 without using synthetic division. Well, I've done more than just showed that negative 1 works. I have also factored out x plus 1. Remember, every root has a factor. If negative 1 is the root, x plus 1 is the factor, and I have divided it out. This set of numbers represents the coefficients on a new polynomial. This is what we refer to as a depressed polynomial, meaning that the power has been dropped by 1. So now, because there's only three numbers, it represents a quadratic. So once I get it depressed to a quadratic, I get to run the quadratic formula. So I'm going to run the quadratic formula with a equals 2, b equals negative 7, and c equals 6. I get 3/2 and 2. So that was a whole lot easier than trying all of my numbers. I find a number that works, I quote-unquote depress the equation, And if it's a quadratic, I switch to the quadratic formula. Now, if I were listing my roots, yes, 3/2 and 2 are roots, but don't forget to list that -1 that you found earlier. So my roots for this polynomial are 3/2, 2, and -1. Okay, so the irrational roots theorem. Again, I'm not going to bother to read it word for word for you. Right now would be a good time to pause the video and write it down. But basically, the irrational roots theorem says that if you have rational coefficients in a polynomial, which you will in all of your work, you're going to have rational coefficients, then irrational roots occur in pairs. And those pairs are conjugates. A plus b square root of c, a minus b square root of c. And you're kind of used to seeing that already because the quadratic formula gives us plus or minus. It gives us irrational numbers in pairs. Okay, so here's a step-by-step process for identifying all the roots of a polynomial equation. First, make sure it's in standard form equal to 0. Divide by x if you do not have a constant term. That means that if you don't have a number without a variable at the very end, divide by the variable so that you have that constant. If you have to do this, remember one of your roots is x equals 0. List your p over q values. Now don't try to sidestep this step. Don't try to skip this and say, oh, I can keep it straight in my head. List them. If you don't list them, you will very likely forget one or miss one, and you'll be forever struggling without a complete p over q list. And then you have to start trying them to find some that work. As you find p over q values that work, you depress the equation to a quadratic. That means that we're lowering the power using that synthetic division. Once it's in a quadratic form, use the quadratic formula to find your last two roots. So, let's do that on this one. Here's a polynomial. My p over q values are plus or minus 1, 2, 3, 5, 6, 10, 15, 30. Notice no fractions because my q values are just 1. So it's always nice when it's just a 1 right here. Now, I am not going to try all of these. I am going to show you one that works. Stay away from the really big numbers. Quite honestly, I hardly ever see the big numbers work. Not saying that they can't. I'm just saying that you hardly ever see them work. Stick towards the front sum. Oh, here's one from the middle that works. -6 works. I run synthetic division to depress the equation. I'm down to a quadratic after one step. Now I run the quadratic equation on this, and I get plus or minus the square root of 5. So again, my irrational roots happen in pairs. I have the positive square root of 5 and the negative square root of 5. So all of my roots are -6 and then the square root of 5 and the negative square root of 5. Now here's one of these weird ones that we're going to factor like a quadratic. If you can factor it, if you can skip the whole p over q stuff, do it. We're going to factor this like a quadratic. We get x squared minus 5 times x squared minus 4, plus 4. This one's going to create some irrational roots. This one's going to create some imaginary roots. Set them both equal to 0. Move the 5 over, take the square root. Move the 4 over, take the square root. I get x equals plus or minus, because they happen in pairs, plus or minus the square root of 5, or plus or minus 2i. So a pair of irrational numbers and a pair of complex numbers. Okay, so it's time for you to try some of these on your own. I know it's a lot, but you can do this. Work the system, find your p over q's, depress the equations, use the quadratic. You can do this. I'll see you in class, and I'll see you online.